This video is part 4 of Chapter 4, Learning for PSY 110S, the Psychological Sciences. So we've covered classical conditioning and operant conditioning. In early behaviorism, and that includes the work of B.F. Skinner, the work was often described as quote-unquote radical behaviorism, which isn't a particularly precise way to talk about it. But the way in which it was perceived to be radical was that these behaviorists argued that you should not look beneath the surface. You only should, as a scientist, look at overt, measurable, observable behavior. That quickly became a little too restrictive because even with rats and pigeons, especially if you move up the levels to primates and other kinds of smart species, so-called smart species, and then include humans, you really can't avoid looking under the hood. You have to look at cognitive factors, you have to look at motivation, you have to look at emotion, you also have to look at evolutionary readiness as well. So that's what we're going to cover in this part of the chapter. We'll start with motivation. Motivation, broadly speaking, refers to factors that are both internal and external, that increase the likelihood of a behavior or increase the likelihood that an organism is going to move toward a goal, or exhibit behaviors that will help the organism achieve the goal. So, if I'm working with my dog on learning something new, I need to find a way of motivating the dog. Some dogs are really into training, some dogs are really food motivated, some dogs are not food motivated. You have to use some other means of motivating them. So part of what being a good dog trainer is about is discovering who your dog is and what motivates them. Same with people. If you're working to change people's behaviors, you really have to think about what motivates them. How can you take advantage of some of their internal factors like personality, previous learning, previous experiences, as well as external factors like what kind of reinforcers you're using that can shape that behavior and get the organism to move in the direction that you want. There are a lot of different theories of motivation. One of the oldest is called drive reduction theory, which is based on, really basic biological needs. So like hunger. If you're hungry and food is offered as a reinforcer, that's very motivating. Whether you're a person or a pigeon, doesn't really matter. If you're hungry, food becomes a motivator. So the behavior is motivated by the desire to reduce the drive associated with hunger. Another theory is called incentive theory, and this certainly relates to humans and the way they are motivated to learn. This theory argues that an organism is kind of pulled into behaving in a specific way when the incentives are set up to make it rewarding for them. So generally, by manipulating the environment, manipulating the stimuli in the environment, you're creating an incentive for the organism to do the task. So in the scent training example, if you provide a paired situation between the scent that you're training the dog to seek and treats that they already like, you're providing them with an incentive immediately to pursue that goal. Now in humans, you might have more elaborate incentive systems like rewards that are public, so that you get kind of double rewards. It's not just the completion of the task and the reward that you get, but also the public recognition. So those can be more complex incentives. There's also arousal theory. And in this case, and humans are definitely like this, so are dogs. Some people, some dogs are very, very energetic, very challenge-oriented. They constantly need to be in a state where they're energized. So I'm thinking, for example, of a hardworking border collie. You've probably seen videos of border collies working sheep or doing fantastic tricks on TikTok. As a breed, border collies tend to be very, very arousal driven. They're high arousal dogs. They like to be entertained. They like to be excited. They like to be working. Belgian Malinois are another dog breed like this. They're very high intensity. They like to be in a high arousal state. So they like to be challenged. And some people are like that too. And you can take advantage of that. You can use the preferred level of arousal for the organism as an incentive, as a way of reinforcing their behaviors as they go along. So basically, according to arousal theory, behavior is motivated by maintaining the desired level of arousal for the organism, whether you're talking about different dog breeds or different kinds of people. Now, one rule that you can pay attention to with arousal theory is what's called the Yerkes-Dodson law. And basically, if you're trying to choose a level of reinforcement associated with a particular level of arousal, you need to first figure out what is the optimal arousal level for the organism you're dealing with. So, because if you get too high a level of arousal, you can overwhelm the organism. If it's too low, they're bored and they're not engaged. So whether you're talking about people or animals that you're training, you have to find use some tasks, do some experimenting, and figure out what's that optimal level of autonomic arousal that keeps the organism interested and engaged. For humans in particular, there's a difference between what's called intrinsic and extrinsic motivation. Intrinsic motivation is internal. Extrinsic motivation is motivation coming from the outside. So let's start with extrinsic motivation, which is basically you're doing the behavior in order to receive a reinforcement from the outside. So I'm thinking back to when my kids were little. There was this reading program that was offered by Pizza Hut. And if you brought in this sheet of paper documenting how many books you read, you could get a personal pan pizza. So it was this big program. And, you know, being a psychology instructor, I was looking at it and going, oh, this is a problem. Because they thought, you know, the originators of the program thought, oh, this will get kids really excited about reading. What it'll do is really teach them that they love reading because they're getting pizza. Well, the problem was that kids would read the required number of books as fast as they could, and then they would get their ticket that allowed them to get their pizza. As soon as the program was over, they tended not to want to read for pleasure. They were really focused on the external reward. So what the designers of the program wanted was to increase intrinsic motivation, which is the desire to do an activity simply because you enjoy it, simply because you like it. And in that case, reinforcement is provided directly through the performance of the activity, not by external rewards that come after you perform the behavior. So the situation that I was describing before with the book it rewards with personal pan pizzas from Pizza Hut is something called the over-justification effect. And your authors describe this as a decrease in intrinsically motivated behavior after the behavior has been reinforced extrinsically in a very obvious way. And then you take the reinforcement away and the level of the behavior just declines. So what Leppergreen and Nisbet did in their study, which is now a classic study, they had children, elementary school age children, who enjoyed drawing. So they were using felt tip markers and they were drawing pictures. For some of the children, they were given prizes every time they drew. So, you know, before they started, they got a baseline level for all kids in the study of how much they were drawing. some of the kids were given very explicit prizes, which is an extrinsic reward for playing with the pens and drawing. The other children in the control group were not given prizes for playing with the pens. They waited a week, no prizes were given to anyone, and the children who had not received the prizes the week earlier still continued to play with the pens. The kids who were given the explicit rewards, their level of playing with the pens declined. Now, the explanation was that the children were very aware of the idea that their behaviors were being tied directly to the receipt of these external rewards. So essentially what was shifting was their personal explanation of their own behavior. So the kids in the experimental group who were given these rewards, if someone asked them, why were you playing with the markers? Why were you drawing? They would say, because I get prizes from the prize box. The other kids who were not given rewards, when they are asked, why are you drawing? Because I like drawing. So they essentially, it's called over-justification, because the kids in the experimental group, they have two reasons. One of them is very obvious, the external rewards. The other is less obvious, your previous desire to draw because it's fun. So you're over-justifying a behavior that was already reasonably well motivated by attaching a reward on top of it. So this extrinsic motivation is overloading and providing too strong an explanation such that when the rewards are removed, the behavior actually declines. Now, another element that you have to pay attention to if you're thinking about using operant conditioning to train behaviors is what are the limits biologically of the organism that you're training. In the 60s, well, it still happens today, although with CGI and all kinds of stuff, we can create images of animals doing all kinds of entertaining things without actually having to use animals. But in the 60s and 70s, you actually had to use animals. And it was very common for people who were making commercials or making movies to try and use trained animals who could do tricks in their work. There was a set of researchers who also partnered with animal trainers in the Hollywood space. They wanted to show that there are some times when you have to pay attention to the species and the task. And one example they gave was a commercial they were trying to make using pigs. Because, piggy bank, it was a banking commercial. And they wanted to train the pig to pick up an object from the ground that looked like a coin, carry it to a piggy bank, and put it in. And what happened was that the pigs would get really obsessed with picking up the coin, but then dragging it across the ground back and forth, as if they were cleaning it, because that's how they root for their food in the wild. It's a biologically predisposed pattern of behavior, and no matter how much training they did, they could not get the pigs to stop rooting with the coins that they were playing with. Now, here's another example.
Conditioned taste aversion is the rebel of classical conditioning, since it breaks some well-established rules. Let's start with a real-life example. For many people, this pizza probably triggers thoughts of yumminess, but for other people, like Sherry, it provokes strong feelings of nausea. Why does Sherry feel this way about pizza? Many years ago, she had some pizza for lunch, and later on that day suffered from a nasty stomach bug and ended up spending the next 24 hours in the bathroom. Even though it wasn't the pizza that caused this illness, she now has a lifelong aversion to it. She hasn't eaten pizza since. This experience is also common in people who've experienced gastrointestinal illness from food poisoning. This incredibly strong, learned association between illness and food is known as conditioned taste aversion. Conditioned taste aversion is a learned avoidance of a particular taste, specifically when nausea occurs after food is eaten. If we compare what happened in Pavlov's original experiments with Sherry's learned aversion to pizza, we can see similarities. In both situations, there's a stimulus that automatically triggers an involuntary response. Meat makes dogs drool, and stomach bugs make us bark. In Pavlovian terms, these are the unconditioned stimuli and unconditioned responses. In both types of learning, there's a stimulus that occurs before the unconditioned stimulus, which on its own shouldn't trigger this response. The pairing of these stimuli, the bell and the pizza, with the unconditioned stimuli results in them taking on new meaning, and they can then trigger the responses on their own. In Pavlovian terms, these newly learned triggers are called conditioned stimuli, and these learned reactions are called conditioned responses. Let's take a moment to review Pavlov's fundamental rules of classical conditioning. First, multiple pairings of the conditioned stimulus with the unconditioned stimulus are necessary in order for the conditioned stimulus to take on the association. Second, the conditioned stimulus and unconditioned stimulus must be presented close together in time. These rules are based upon a mountain of laboratory research observed in meticulous experiments under tightly controlled lab conditions by Pavlov and others. However, Sherry's conditioned taste aversion to pizza did not appear to require multiple pairings. In fact, there was only one time when the pizza was paired with illness. Also, Sherry ate the pizza hours before the nausea set in. So conditioned taste aversion appears not to fit neatly with the research on classical Pavlovian conditioning. Of course, Sherry's learning happened in messy real life with a slice of pizza and a tummy bug, so it's useful to look at this phenomenon in a laboratory setting. Conditioned taste aversion is also referred to as the Garcia effect, after John Garcia, whose classic research first investigated this. Garcia accidentally stumbled upon his now famous research studying the effects of radiation exposure. He noticed that rats responded to low levels of radiation with reduced feeding as a result of gastrointestinal upset. Therefore, he set out to ask two questions. Can rats be conditioned to avoid a sweet taste, which rats ordinarily love, if it's paired with radiation, which makes them sick? And, if so, how long does this food aversion last? So this is what he did to test his hypothesis. There were 6 groups of rats, exposed to one of 3 irradiation conditions: no radiation control group, low radiation, and high radiation for a period of 6 hours. For the 6-hour radiation period, rats were either given access to regular water or water with the artificial sweetener saccharin. Keep in mind that there are 2 independent variables: the level of radiation, indicated by the colors, and the fluid they were given while exposed to the radiation, which is indicated on the water bottles. After this 6-hour conditioning period, rats were given a choice between 2 drinking bottles, one with water and another with, you guessed it, saccharin water. The dependent variable was how much of the saccharin water the rats consumed. Like humans, rats like things that taste like sugar, so ordinarily they prefer sweet-tasting saccharin over plain, unflavored water. Since radiation produces gastrointestinal upset, Garcia hypothesized that the rats might associate their illness with a sweet taste and avoid it in the future. And this is what he found. The main measure was the percentage of saccharin water the rats drank when given a choice, shown here on the y-axis on the left. Rats that got water during the conditioning session drank mostly saccharin water afterwards, close to 100%, regardless of whether they were in the control group or the radiation group. This strong preference for sweet saccharin was also similar in the rats that got saccharin water during training but were not irradiated. Since they didn't get sick, they didn't have an unconditioned stimulus to associate with the sweet taste. The interesting part of this experiment is that rats who received saccharin with radiation avoided drinking saccharin water later. The more radiation, the more they avoided the sweet-tasting water. Garcia tested saccharin preference later in these same rats and found that there was a strong aversion that lasted 30 days, which didn't go back to pre-irradiation levels until 60 days later. This seems like a tidy experiment, but you might say, hey, wait a minute. Did the rats given water while irradiated, these ones here, avoid water? Does their saccharin preference indicate that they like sweet taste, or is it that they now actually hate regular water? Garcia thought otherwise, so he did some more experiments about the nature of the relationship between the different types of conditioned stimuli and nausea-inducing and other aversive events. In classical conditioning experiments, animals have a whole host of sights, sounds, smells, and tastes in the environment to choose from. So which ones get chosen for conditioned taste aversion? In another experiment, Garcia and colleagues exposed the rats to a few different types of conditioned stimuli when they drank. In a pre-test, they either got water with a sweet taste of saccharin or a bottle when licked that turned on a bright light and a noise. They then presented these rats with different types of aversive events during conditioning. Rats were randomly assigned to have all of these stimuli paired with either nausea-inducing X-rays or painful electric shocks. After conditioning, there was a post-test where rats were given a choice: sweet water or the tasteless but bright and noisy plain water. This way, they separated the conditioned stimuli to see if they were preferentially associated with particular types of aversive unconditioned stimuli. The X-ray experiment is shown on the left in blue, and the shock experiment is shown in red on the right. In both cases before conditioning, rats drank roughly equal amounts of the sweet saccharin water as the bright noisy water, showing no strong preference for either. However, after conditioning with a different aversive unconditioned stimuli, there was a clear distinction in preference depending upon whether the rat had been conditioned to pain or illness. The rats in the nausea condition clearly avoided the sweet saccharin water, while those in the pain condition avoided the tasteless but bright and noisy water. This shook up the learning world, which firmly supported the idea that conditioned learning is universal, so it shouldn't matter which stimulus is paired with what. Garcia showed that our sense of taste is more easily conditioned to illness, while our sight and hearing are more easily conditioned to fear. Garcia's findings sparked all sorts of debate on Skinner's and Pavlov's perspectives on learning. They maintained that the processes of associative learning were universal and general, and that any arbitrary stimulus could be used as conditioned stimulus. But these conditioned taste aversion experiments showed otherwise. Garcia's findings fit with an evolutionary perspective on taste aversion in that it's important to learn which taste might make us sick. It's valuable to quickly associate tastes and smells of particular foods with nausea in order to avoid contact with those potentially harmful substances again. This knowledge has been used to deter predators, such as coyotes, from eating livestock by placing carcasses laced with lithium chloride, a non-lethal chemical that produces nausea, near the livestock they want to protect. Many farms have dramatically reduced coyote predation on sheep herds and turkey farms without trapping or shooting the predators, since the predator's own natural food aversion keeps them away. Hopefully that gives you a clear idea of the phenomenon of conditioned taste aversion.
So what's been shown here, just like with the biological predisposition for pigs to root their food, we also have biological predispositions to pay attention to cues in our environment for certain kinds of information that impacts our survival. So what Garcia and Kelling were able to show was, twofold. Number one, if you associate a particular taste with getting sick, you're going to avoid that particular taste because it may make you sick again. If you're out in the wild and you're feral and you eat something and get sick afterwards, then you're going to avoid that thing. Now, the response that the rats in their work had to quote-unquote bright noisy water, if something is going to be scary in your environment and you're a rat, it's more likely to be something that also makes noises and can be seen. So fear arousal tends to be more connected to those kinds of cues. So it makes sense, evolutionarily speaking, that you would be attuned to those triggers. Now, with my example earlier of the pigs that they were trying to train, is actually an example of instinctual drift. And this is a tendency for animals to kind of drift back after they've learned an operant response, but that if the response is kind of tethered to an innate behavior, they're going to drift back to that innate behavior. So, for example, the pigs, they could be trained to pick up an object and put it in a piggy bank. However, their tendency to play with their food and try and get dirt off of the roots of something they've pulled out of the ground, they will drift back to that behavior and it will interfere with their performance on the task. So what's happening here is that you have biologically instinctual responses that sometimes can get in the way of conditioning other kinds of responses that the organism is fully capable of doing, but their instinctual patterns, their biological predispositions toward certain other behaviors can sometimes interfere. So what this suggests is that there are some limitations. Basically, your instinctive behaviors maybe set guardrails up as to exactly how you will be able to learn a task. Now, here's a concrete example of instinctual drift.
This video shows segments of recordings taken during approximately 20 daily 1-hour training sessions. During each session, a young raccoon was placed near a wooden bank in an enclosed arena. The training objective was to entice the young raccoon to pick up a red poker chip and then deposit the poker chip into a slot in the bank. 2 10-week-old raccoons, Stinky and Scampy, served as subjects. During the course of a 4-week training period, the raccoons were awarded with a morsel of shrimp for picking up the red poker chip. This was easily learned. Our intention was to require more of them as training progressed, so they would receive the morsel of shrimp for picking up the coin, carrying the coin to the bank, and depositing the coin into the bank. They quickly figured out that picking up the red poker chip was promptly rewarded with a morsel of shrimp. But after a few pairings of the poker chip with the shrimp reward, the raccoons began to have problems. They began to lick, gnaw, chew, and play with the poker chip, sometimes endlessly, so that few poker chips were deposited in the bank. This resulted in the loss of most of the available food rewards. To remedy the situation, the slot in the bank was altered in several steps into an upside-down T, into a larger square hole, and finally into a larger square hole with angled ramps, so that merely touching the poker chip placed on the ramp would roll the chip into the hole, dropping it into the bank. All of this was to no avail. The raccoons were not happy to see the poker chip slide into the hole and drop into the bank, even though this immediately resulted in the payment of the shrimp reward. Instead, upon seeing the poker chip resting on the ramp, they removed it from the ramp, rescued it from the sliding into the hole, and began to play with it. Poker chips that were directly deposited in the bank by the camera crew to give the raccoons an idea of what they should do were promptly removed from the bank to be played with. After several additional weeks, with no discernible progress, we were forced to give up. The raccoons taught us a lesson. They taught us that only a few pairings of the red poker chip with the shrimp reward were sufficient to cause the raccoons to form an association between the chip and the food. They now behaved toward the red poker chip as though it were food. They approached the chip, picked up the chip, and placed the chip into their mouths, licking, gnawing, chewing, and rubbing and hoarding the chip as though it were actually food. They did this even though the behavior served no purpose other than to reduce dramatically the number of food rewards that the raccoons would receive during the training session. Scientists call this type of behavior sign tracking. Sign tracking is important because it provides us with a way of understanding the conditions under which behavior escapes self-control and defies self-will.
Now what this shows, and this is actually a modified reproduction of a study that was done I think it was in the late 60s or early 70s, where animal trainers were trying to use raccoons in a very similar kind of TV commercial to what was attempted with the pigs, where they wanted to show the cute raccoons picking up an object and depositing it in a box with a slit. I can't remember if it was a banking commercial or what, but they were having to put an object in a slot, and they were able to train the raccoons pretty quickly to pick up the coin, the object, move to the box, and start to put the object through the slot. Pretty quickly, though, what started to happen was that the raccoons, just like in the video you just watched, would kind of dip the object through the slot, but not relinquish it. Even though they were using very, very high value reinforcers, food reinforcers, the raccoons were just too enamored with the idea of washing their food, which was what the researchers described it as. In the wild, raccoons can sometimes be found to find something to eat and then douse it in water, dip it in water, and then eat it. Or if it's very dirty, pound it on the ground, clean it off, and then eat it, whatever. They have a tendency to want to mess with their food. And, what's described in the video as sign tracking is also referred to as instinctual drift, where you're just sort of backtracking, and breaking that instinctual pattern is going to be, virtually impossible. So what the marketers had to do was, if they wanted to use animals in their commercials, they needed to be very careful about the task they wanted the animals to do. They needed to avoid tasks that were going to be interfered with by instinctive patterns of behavior. Now, there's another form of learning called latent learning, and this is learning that occurs but isn't shown until there's a reason, some sort of reinforcer that's coming real soon. So there has to be incentive for the organism to show it.
What's up, All-Stars? Welcome to the School of Ireland. Today we're going to talk about a psychologist named Edward Tolman. During his studies, Tolman came up with a concept called latent learning, which is learning that occurs but does not become apparent until there's an incentive to demonstrate that learning. So I know this definition sounds confusing, but I promise it'll start to make sense once you see a few examples. Tolman keyed the term latent learning after testing how fast rats could run through a maze. He came to his conclusion after analyzing what impact different incentives had on the rat's performance. The first thing he did was split the rats into a few different groups. The first group received a food reward for completing the maze, and the second group, aka the control group, received nothing for completing the maze. So let me ask you this, which of these two groups do you think completed the maze faster? Yeah, this one's pretty obvious. If you said the first group that received a food reward, you're right. It's because they had an incentive to complete the maze faster than the group that didn't get the food. But Tolman didn't stop his experiment here. He also had a third group of rats that was required to run the maze for 10 days without any reward. This meant that this third group of rats wandered somewhat aimlessly around the maze, just like the control group did. But then Tolman did something very interesting. On the 11th day, Tolman gave this group of rats a food reward for completing the maze. What's fascinating is once this third group of rats received a reward, they completed the maze faster than both the other groups. And this is because of latent learning. In other words, this third group of rats knew or learned how to run the maze within the first 10 days. However, this was not apparent until these rats were given a reward or an incentive to demonstrate that they learned how to run the maze. Let me give you another example. Let's say you're trying to train a dog how to sit using only verbal commands, but for whatever reason, it just won't listen. Let's say you've been trying to train the dog for a week and you're beginning to get really frustrated. And then after dinner one night, you see that you have some leftover food on your plate that you decide to pick up and take over to your dog. And then you tell the dog to sit, and it suddenly does so. Well, why did this happen? Why didn't the dog listen earlier? The answer is latent learning. The dog already knew how to sit due to all the training that you had already given it leading up to this point. However, this learning did not become apparent until the dog had an incentive to show it off. Let me give you one more example. Let's say one of your parents drops you off at school every single day and then proceeds to drive off to work. Well, let's say one day that parent gets sick and you have to drive yourself to school. If you can get yourself to school without using a GPS, that's latent learning. You learned how to get to school on your own by watching the turns your parent made every single day. However, this learning did not become apparent until you had to drive yourself, and the reward in this case is getting to school. So those are 3 examples of latent learning. But you should also note that Tolman coined another term in regards to his rat studies, and that is a cognitive map. A cognitive map is a mental representation of the layout of one's environment. Let me show you how this works. I want you to close your eyes, and I want you to visualize in your head how to walk from the front door of your house to your room. Can you do it? Or try this one. Can you visualize the route you would take and all the turns that you would make in order to get to your best friend's house? If you can picture these things in your head, you're using a mental or cognitive map. So that's pretty much it for today. But I wanted to ask you, can you think of any ways in which you have demonstrated latent learning? If so, go ahead and share your experience in the comments. That's it, All-Stars. Please don't forget to check out all the other awesome videos that are on this channel. Make sure you like and subscribe. Have a great day.
So what he's describing there is Tolman's famous research on latent learning. And what it shows is essentially we learn a lot about our environment, whether it's a mental map of that environment or just sort of the structure of when reinforcers are likely or unlikely and so on. So we pay attention to all those things and we learn a lot about that environment. When an incentive becomes clear, we can use that bank of knowledge in order to get the incentive, to get the reinforcer coming our way. Now, why this is important is that those early behaviorists, people like Watson and Skinner, argued that you can't learn without direct experiences with consequences. Tolman proved them wrong by showing that, in fact, you can learn a lot from your environment without getting any reinforcers at all, without any kind of consequences. Because once those consequences get put on the table, you demonstrate that you actually know what you're doing. Now we're going to conclude this chapter with one of the most famous examples of research into what's called social learning. Albert Bandura is most well known for studying modeling and learning through observation. So I'll play this video clip of Bandura's famous Bobo doll experiment and then talk about it.
The segment you're about to see is taken from an early experiment on learning of aggressive styles of behavior through modeling. Children watched a filmed adult perform novel aggressive acts toward a inflated doll, and the physical aggression was accompanied by novel hostile remarks. We later measured how much of this modeled aggression the children had learned just by watching. Now, the measurement of learning of aggression uses simulated targets rather than live ones. For example, to test how well bombardiers have learned bombing strategies, you would use simulated targets rather than require them to bomb San Francisco or New York. The model pummeled a doll with a mallet, flung it in the air, kicked it repeatedly, threw it down and beat it. It was once widely believed that seeing others vent aggression would drain the viewer's aggressive drive. As you can see, exposure to aggressive modeling is hardly cathartic. Exposure to aggressive modeling increased attraction to guns, even though it was never modeled. Guns had less appeal to children who had no exposure to the aggressive modeling. The children also picked up the novel hostile language. The room contained varied play materials.
So that gives you kind of the outline. There's a longer documentary that you can find out on YouTube describing the full study. But basically what Bandura was able to show was that, kind of following Tolman's latent learning idea, the essence of observational learning is that you can show a person a behavior and then give them an opportunity, set up the right motivational context, and they can demonstrate the behavior even though they didn't have reinforcers present when they learned the behavior. So for humans, this is particularly important. It's the way we learn a lot of what we learn about social life and what behaviors are appropriate and what behaviors are not appropriate. We pay close attention to what other people are doing, how they're doing it, and especially whether they get rewarded or punished for doing those things, and what kind of predictors are available in the environment for telling us when and which kind of consequence is going to occur, because that will determine whether or not you're going to exhibit the behavior. So that's really the important part of what Bandura was able to show. So the essence of observational learning in the Bobo doll study was that children were exposed to an adult who exhibited aggressive behavior. Now, the Bobo dolls, I don't know if you can still find these in stores, but we had one when we were kids. They're really funny. They had a squeaker in the inflatable nose, and, it was a really funny thing when you're little to, just punch that nose and squeak it, and, the Bobo doll would fling away and come back because there was sand in the bottom. So basically you had two types of models. You had an aggressive model, and you had a gentle model. Now, both models were exposed to a frustrating motivator. So basically, the adult model is shown some toys and told, you don't get to play with these really cool toys because they're for special people, i.e. you're not special. Now, most little kids have some experience with being told they can't have things that they want. So they get this. They know that this is going to be frustrating. So then the adult goes into the room the kid is watching, and the adult either behaves aggressively or they just find something else to do. And when the kids are later taken to another room and they have been similarly frustrated, so they were exposed to the same kind of motivation that the adults were, that sets up the context, and the kids are given the availability of the toys, including the Bobo doll, and those who were exposed to the non-aggressive model just played with the objects in the room in a non-aggressive way, including the Bobo doll. Those who were exposed to the aggressive model, they tended to be more likely, not all of them did, but many did, they acted out exactly what the model had performed earlier. So basically the behavior of the children was shaped by the model to which they were exposed. And Bandura took this a step further. He wanted to know if the children, these were toddlers, were sensitive to the types of consequences that adults got for their aggressive behavior. Were they punished for it? Were they given no consequences? Were they rewarded for it? And the kids showed that just by watching what happened to the adult, whether or not they should exhibit the behavior or avoid exhibiting the behavior. If they saw a model that had been punished, they avoided it. If they saw a model that had been rewarded, they tended to engage in it more often. So basically, consequences matter even when we are not receiving them ourselves, when we see other people. It's kind of like when you're out on the highway and you see another driver's been pulled over, you're like, aha, this is a speed trap. I will slow down. If everybody is driving 80 in a 70 and you don't see any police presence, you're more likely to just continue driving well over the speed limit because basically all of the other people around you are models and they're not getting consequences. So you're less likely to get consequences as well. Now, what, in one step further, what Bandura was able to show was when he took those children who saw the model get punished, who avoided exhibiting the aggressive behavior and said, hey, can you show me what the model did? You're not going to get punished. I just want to know if you know what they did. The kids were fully able to act it out with a great deal of precision. So that showed that they learned it, but they also learned that there were good reasons for either suppressing or exhibiting the behavior. And that concludes my coverage of Chapter 4.